All right. So I think today we're going to finish up on chapter 7 if we're lucky. Go ahead.
Also, are chapter 5 and 6 study guides due sometime?
Yes. The chapter 5 and 6 study guides have been available for some time, but I haven't made the little thing where you go in and say that you did it available. That is now available, and it won't be due till after the exam. So if you've done the chapter 5 and 6 study guides, just make sure before the end of too long, I'd say maybe before Saturday, that you go on and indicate that you've done it. All right. So we talked last time about integrated rate laws. I believe we got to first order kinetics. This was the situation in which the rate of change, font size, in the product concentration is directly proportional to the concentration of starting material that remains. If you were to plot rate of the reaction, if you can monitor that continuously versus starting material concentration, you would observe something that's linear. Alternatively, you can, let's see, and we said that was the same as the disappearance of starting material. You can isolate variables and integrate to get the following expression, the natural log of the starting material concentration minus the initial concentration of that starting material equals your rate constant times time. And if you want, you can further rearrange that into the more familiar expression that you guys saw in general chemistry. And a key thing you can try to do if you think a reaction is first order, and especially if you can monitor the disappearing starting material, if you want to plot the natural log of your starting material concentration versus time, it should be linear and the slope will be k, right? Or minus k, as the case may be. All right, any questions about that? It's a simple reaction. Starting material converts to products. That is, and does so in an irreversible way, I should say. This is not equilibrium kinetics. This is for a first order reaction where starting material goes to product with a rate k, then there's no backwards reaction. I'm sorry, in my brain I just got distracted because I realized that first order sounded kind of Star Wars-ish. So, all right. Now, of course, reactions can get more complicated. So let's talk about increasing levels of complexity. Second order, the irreversible reactions would involve A reacting with B to give us product P. The rate of appearance of product P is going to be proportional to the concentration of A and the concentration of B. That rate is going to be first order in A and first order in B, but second order overall. And you can develop an integrated rate law for this equation, but it involves algebra and a table of integrals. And the calculus is beyond my current abilities, nor do I really care or expect you to be able to do it. So if you do that math, you end up with an interesting expression that depends on your starting concentrations of A and B, followed by the natural log of starting concentration of A times concentration of B, all divided by starting concentration of B times current concentration of A. And if you plot that versus time, it should be linear and the slope would be k. Now, you have to be able to monitor both the disappearance of A and the disappearance of B as the reaction progresses. That can be a tall order, depending on what experimental technique you're going to use. And so what is often done in these cases is to cheat. And we cheat by doing something called pseudo first order kinetics. Dakota, I saw your hand. What were you going to say?
Yeah, in previous classes where we did second order, it was just a squared, which made the integral.
Sure, right. If A and B are the same, yeah, then it's
right.
trivial.
Yeah, we integrated the -2 power and it became -1 and that's all.
Yep. Yeah, so if it's simpler where two of A just reacts with itself, then that's a little more straightforward to do. This is if A and B are different. So one of the things you can do in a case where you've got a reaction like this and you don't want to have to monitor two things is you cheat by using a huge excess of B such that at any given point during the reaction, B is basically constant. All right? And as an example of what kind of excess gives you this situation, perhaps like tenfold excess B. All right, then the concentration of B doesn't change very much as a function of the reaction. So if we go back to our initial expression for the rate law, K times A times B, we're making this key approximation that the rate's not going to change. The concentration of B isn't going to change very much. So in other words, change in the pen. The appearance of product will equal K times the concentration of A times the initial concentration of B, which is a constant. So you can represent that as K obs, observed rate constant, times A, where K obs, fine print, equals K times B. Okay? So you swamp out B to make it constant. You measure the appearance of product. You measure the rate. You monitor the concentration of A. Now this is where the pseudo first order comes from. Because the B concentration stays roughly constant, now the only thing that's changing is A, and you've got less to worry about. So one of the interesting things you can do, if you want to now know about the order of the reaction in A, you could go back and, the order of the reaction in B. You could go back and swamp out the concentration of A and then make it pseudo first order in B. But alternatively, you can repeat this experiment at multiple concentrations of your starting B, okay? And then you're going to get a K obs versus B naught set of data, and that will allow you to get at the rate constant. All right? Alternatively, you can use pseudo first order kinetics to tell the difference between these two situations. What we've written here is for A plus B going to P. What if it was something like this? How would you be able to observe that that was the case? Well, again, you would use so much B that if we were to write a rate law for this equation, it would be K times concentration of A times the concentration of B squared. But again, if you use a large concentration of B, you can make it first order in A, And then as you vary the starting concentration of B and measure K obs, you would expect the relationship between K obs and starting B concentration to be quadratic in nature, right? So that's a situation where you can tell by doing first order kinetics and then doing that, measuring K obs at multiple starting B concentrations, you can tell whether the reaction is first order in B or second order in B, and so on. I'm not sure I explained that very well. Questions about that?
So the slope is key.
That's right. Up here, the slope would be K. The slope of K obs versus starting B concentration. Down here, for the reaction that's second order in B, there'd be a quadratic relationship, and so I'm not sure. You would fit the data and you could figure K out. Yeah.
So like this is what we do in freshman Gen Chem, where they give us the tables of all the different concentrations of the stuff, and you see its relationship to the K value, and you figure out the order.
Exactly. Yep. You've done this in Gen Chem before. Yep. All right. So, and again, that's for irreversible reactions. But a lot of the reactions that we care about in organic chemistry have steps that involve equilibria, and that can complicate things. So we're going to talk now, sort of break away from first order, second order, pseudo first order experiments to talk about kinetics of approach to equilibrium. Now, you may have heard me say, you may have heard the word equilibrium and thought that you could sigh a large sigh of relief and not worry about kinetics anymore, because of course, if something's at equilibrium, the kinetics aren't changing anymore. For example, for the simple conversion of A into B with a forward rate constant and a reverse rate constant, at equilibrium, the rate of change of A equals 0. Am I doing that right? Hold on. I think at equilibrium, the rate of change of the reaction overall, the overall rate of change in A and in B is equal to 0. But the reason for that is because the rate of change in A is equal to and balanced by the rate of change in B, right? So the forward rate is as fast as the backwards rate, or alternatively, Kf times the concentration of A equals Kr times the concentration of B. And I'm not sure what the sign relationships ought to be. I think, why am I getting confused here? I think they have to be opposite. Yeah?
Well, wouldn't A be negative because it's disappearing?
Right. But then B, why is this confusing to me? The forward rate and the backwards rate are equal to each other. Yeah. I think that's right. Right. I guess the best way to express this would be the disappearance of A is minus Kf times A, and the disappearance of B is minus Kr times B. And if they're both disappearing at the same rate, then nothing's happening. All right, so at equilibrium, there's really nothing to show here, folks. But what about the approach to equilibrium, and how do we talk about that? So we're going to define a little variable x. This is the extent, get it, of reaction, or alternatively, the amount of A that has been depleted at time t, or the amount, alternatively, the amount of B that has appeared at time t. So at any point in time, your concentration of A equals your starting concentration of A minus X versus your concentration of B equals your starting concentration of B minus X. This is starting to look a lot like how you set up equilibrium problems in Gen Chem, except it should be plus, right? Because X is A disappearing and B appearing. So if we think about the rate of change in X, that extent of reaction, as we approach equilibrium, that number is going to go to 0. But at any given time, the rate of change in X should be the forward rate times the concentration of A, which is really just A naught minus X. And because we've said X represents the amount of A that has disappeared in the reaction, that's going to be balanced by the reverse rate of the reaction, which is B naught plus the concentration of X. That's a little bit of a tough jump. The overall rate of change in the reaction is equal to the forward rate minus the reverse rate. And we're not at equilibrium here. Okay. And we'll be at equilibrium when dx dt equals 0. So you can do the algebra and the integration, or rather it can be done because I can't do it. And you end up with an expression that doesn't look like it's made our lives any better. All right, I'm going to write down this expression and we'll talk about what it means. But don't worry, because we're going to simplify it, and what we really want to take out of here is just a qualitative conclusion. And this equation is in your book, so you clearly don't have to memorize it. Okay. So if we take the natural log of our rate constant times our starting A concentration minus our reverse rate constant times starting B concentration, same things in the denominator, only we also have the forward and reverse rate constants added together and multiplied by the extent of reaction, we get, again, an expression that's linear in time, and it's related to the sum of the forward and reverse reaction rates. Now, this isn't really simple enough to understand qualitatively, so we're going to simplify it a bit. We're going to say that at equilibrium, a certain amount of X will have converted and it will stop changing, and we're going to call that the equilibrium value for the extent of the reaction. All right? We also know that at equilibrium, the forward and the reverse rates are equal. And furthermore, at equilibrium, therefore, concentration of A should equal starting A minus extent of X at equilibrium, and concentration of B should equal starting concentration of B minus extent of reaction at equilibrium. So if you substitute what I highlighted in purple for the concentration of A, and if you substitute what I highlighted in orange for the concentration of B, and then you rearrange it a little bit, you can show that the following has to be true. And this is one of those cases where the algebra may not be obvious unless you know where you need to end up, and so I wouldn't expect you to derive this independently. But now, conveniently, we found something here that appears in our complicated expression up top. And this is going to allow us to make all kinds of convenient cancellations. So we're going to substitute this for whatever is pink above. So Kf plus Kr times extent of reaction at equilibrium divided by that thing again, Kf plus Kr times extent of reaction at equilibrium minus, and I'm sorry, I'm going to have to move this, all equal to Kf plus Kr times T. Aha! Anybody see what we can do? Yes? Where did I replace the concentration of A and the concentration of B? Good. We said at equilibrium, the forward rate of reaction has to be equal to the reverse rate of reaction. So we redefine the concentration of A as two constants at equilibrium, and we plugged it in there, and then we plugged this in there. Rearrange in algebra to get this expression, and then we're going to substitute here in blue for everything above that was in pink. Math. So now that we've done that, what do you notice about the left-hand side of our new equation? That's right. Above, that expression was useless to us because in order to plot anything, we had to know what Kf and Kr were. They were on both sides of the equation. We can't do anything with that. But with this convenient substitution, we now cancel out the forward and reverse rate constants on the left-hand side of the equation. So now all we've got over here is extent of reaction at equilibrium, which we can measure in the numerator, and in the denominator, again, extent of reaction at equilibrium, and then measured extent of reaction as a function of time. And the rate constant is just K obs times T, where K obs equals forward rate plus reverse rate. So that's a general observation that you can, and go ahead, Austin, yeah.
So we're treating the concentration of X, so that's essentially a constant here,
Yep.
even though we don't know what it is.
We can measure it at equilibrium, yeah. We'll know that if we compare concentrations of A and B at equilibrium with the starting concentrations we had.
And then just concentration of X with no subscript, that's our,
Yep.
our main here.
Yep. Yep, so in blue are things that are constants, and here is our, I don't know, here is our independent variable. No. Yes. We watch time, and well, I don't know what we watch. What we would do is we would plot the natural log of this expression, having monitored the concentration of X versus time, and that plot would be linear and give us the observed constant. Then, if you know what the equilibrium constant is, remember equilibrium constant is equal to forward rate divided by reverse rate, then you can tease out what the forward rate and the reverse rates are. Why am I spending time on this? It turns out I had to do this in my postdoc. I had to measure A and B were not separate molecules, they were two different conformations of the same molecule, the folded protein versus the unfolded protein. And we were doing an experiment to measure the rate of protein folding where you take an equilibrating mixture of the folded and unfolded protein at a given temperature, and then we'd shoot a laser at it to rapidly increase the temperature, an infrared laser that would rapidly, instantaneously increase the temperature, and then we would watch some fluorescent signal from the protein as the protein adjusted from the old equilibrium to now what needed to be the new equilibrium. And we could measure a rate constant for that process, but determining the forward rate versus the reverse rate relied on this key point here, that the rate of approach to equilibrium is the sum of the forward and the reverse rates. And I had to take it as an article of faith back then. I think I tried to derive it and failed miserably, and so I'm delighted that all of a sudden it's here. It's always convenient when you learn that something you thought was true actually is. So there you go. Questions about that? Again, the most important rule of thumb there is just that the approach to equilibrium is the sum of the forward and the reverse rates. Yeah, Kim.
So, just to clarify this, you measure the equilibrium constant, you could measure the observed rate constant, and that gives you two equations, two unknowns, to parse out K forward
Yep.
and K reverse.
Yep. Right. To just say that again, you know what the position of the equilibrium constant is. You know what the observed rate constant is. Based on that, you can, two equations, two unknowns, figure out what the forward and the reverse rate constants are. Yeah.
Did it go through all this natural log step just to show where this comes from? Because the equations down at the bottom right seem self-evident.
They are, but
Where's the forward and reverse?
they are, well, the approach, the expression, the approach to equilibrium should be the sum of the forward and the reverse rates is not self-evident. That fell out of integration of this equation.
Oh, how is that not self-evident? Because aren't the only directions the reaction can go forward and back, and sum them together, you find the net reaction rate?
I suppose it makes sense, but I'm not following that logic makes it necessarily so. In retrospect, of course, it's self-evident. Yeah, I don't know.
Yeah.
It's a good question.
Makes you wonder how the observed reaction rate cannot be the sum of those two.
Well, conveniently, mathematically, it is. So, whether self-evident or not, it is true. That's interesting. Truth doesn't care if it's self-evident. It just is. All right. So, the rest of the chapter is a horrible mess of possible more and more complicated kinetic expressions. I think we could go through all of them, though I'm not sure how useful that would be. It's probably easiest if we go through some of this with an example. So, I'm going to introduce the idea of something that we call steady state kinetics. You heard about this before? Is this a Gen Chem subject or is this a biochem subject?
They did in Gen Chem somewhat.
Okay. And again in PChem. Okay, so in steady state kinetics, the situation is you have a high energy intermediate I, and it's in a shallow well, and therefore, and you're also going to assume that I has fairly low barriers to go back to product. Oops, not good, Joshua. To go back to starting material or on to product. So I has low barriers to both A and P, but the step going from I to P is irreversible. Okay? All right, so consider the following scenario. We have A equilibrating with I, And then we have I, and then we have I reacting with B with some rate constant K2 to give you P. All right, so this is, I suppose, we just didn't want to communicate that A broke apart into I plus B, so you got to bring B in here, right? Okay. One of the things we're going to assume is that because I is so high in energy, that the concentration of I at any given time is small. And if the concentration of I is small, it's an intermediate, it's high energy, it shouldn't be very large, then necessarily any rate of change in I is also small. And we're going to approximate it as 0. That is the steady state approximation. During the reaction, for most of the time, the concentration of the intermediate doesn't change. Is that, you okay with that? So we would say that the concentration of our product should be equal to this rate constant K2 times the concentration of B times whatever the concentration of our intermediate is. And then we're going to make the assumption, mathematically this is what the steady state approximation is. The rate of change of I is 0. So now we're going to write all of the possible things that could contribute to the rate of change of I, and we're going to set them equal to 0. So I could increase by conversion of A into I, and the rate for that would be K1 times A. Similarly, I could decrease by conversion of I right back into A, so that would be K minus 1 times I. Is that okay so far? And then the concentration of I could decrease by conversion of I into P with the rate K2 times the concentration of I times the concentration of B. It's delightful when we have an expression like this that we can set equal to 0, because we're going to rearrange. Today's theme is fun tricks of algebra / calculus to eliminate things we don't know. We're going to rearrange this equation, put I and isolate the concentration of I as a variable. Not going to do that algebra. It's not hard, and you can convince yourself that what I'm going to show you is the case. I equals K1 times A divided by K2 times B. Oh, you know what? I made a critical error. There should be a minus sign in front of that K2, right? We're talking about I can appear by A converting into I, which is why this is positive. I can disappear by I converting back into A or by I converting into P. I am sorry for that. That sign is negative. Got that? Okay. So in the denominator here, we have K minus 1 plus K2 times B. Basically, and we can make this more and more complicated, but in the numerator, we're going to have the ways in which I can be formed, and in the denominator, we're going to have the ways in which I can be gotten rid of. We now have an expression for I that depends on, we don't have to know I anymore. All we have to know is our concentrations of A and B, and then these rate constants. Okay? And now we can take what we've discovered for what the concentration of I is and plug it back in there. So now our appearance of product no longer requires us to know anything about I. It is simply this, K2 times K1 times the concentration of A times the concentration of B divided by K minus 1 plus K2 times the concentration of B. All right. And if you look at that overall rate expression, what we might observe depends on the conditions. It looks like the reaction should be first order in A, and it looks like the reaction should have a more complicated dependence on B. If, for example, the term, so let's play around with some of the implications here. What if K2 times B were much, much greater than K minus 1? Either because the B concentration was so high, and remember the B is the second reactant that we're putting in there, or because K minus 1 is so low. What would that do to our overall expression? Right, so I guess we need if, comma, then. That would cause us to get rid of the dependence on the K minus 1. And then all of a sudden, we're going to take out our fun cancellation arrows. All of a sudden, rate doesn't depend on B anymore. It's just first order in A. Okay? In contrast, if somehow K minus 1 is much, much greater than K2 times B, then you're going to see the expression look more like this. K2, K1, divided by K minus 1 times A times B. And in that case, it might look like this reaction was just a regular second order elementary step reaction. So chemists will often use the steady state approximation to design experiments that will tell them something about the mechanism. For example, if this proposed mechanism makes the prediction that you should be able to remove the dependence on B if you got enough B there. Okay. There's a classic example of this that, yeah, go ahead, Kim.
I remember that bottom one, like that's also the rate law that you provide to do pre-equilibrium assumptions.
Is it?
Yeah.
Okay. Oh, hey! That's cool.
Yeah.
So what Kim is saying is this is actually the rate law for a fast pre-equilibrium. Yeah. And in fact, that's K2 times equilibrium constant for the first step, right? Times A times B. All right. Cool. Independently driven. Sounds like I'm saying driven. All right. We're going to make this situation just a little bit more complicated. I'm not going to derive the steady state approximation rate data, but I do want to show you this because it's going to give you the answer to why the SN1 reaction looks like it's unimolecular, even though you got to have nucleophile there to make it work. So to set that up, we need to create the following situation where A converts into intermediate plus product 1, and then I goes on to react with B to give product 2. That actually isn't going to change our rate equation that much, but I will show you, given the steady state approximation, what the rate of appearance of our product is. It equals K2 times K1 times A times B divided by K minus 1 times product 1 concentration plus K2 times B. So it's basically the same thing. This just reflects that the backwards rate of our reaction now depends on the concentration of product that we have there too, right? Okay. So this creates an interesting situation because there are sort of, depending on what our concentration of B is that we're adding at this stage, we'll see different behavior. So imagine that B concentration is very, very small. Okay? If the B concentration is very small, then we expect the second term in our denominator to disappear, and we would expect to observe a reaction that is first order in B. And especially if we did a steady state approximation where we maxed out A so it wasn't changing a lot, we would begin to see in a graph a linear dependence of our observed rate on the concentration of B. In contrast, if B has intermediate values, then we have the full-on expression here where it's somewhat less than first order in B because you've got a B concentration term in the denominator. And then finally, when the B concentration is huge, then your expression for the rate law gets rid of that, and actually the impact of B cancels out entirely. So when B is huge, now the rate is independent of B. So if you were to try to do this reaction using a constant and high concentration of A and then varying concentrations of B starting B and measure the observed rate constants, what you would see is an initial region where the rate was linear in B, then it would start to be less linear in B, and then as B builds up, it would be independent of B. And we can, this is region 1 where B is small, region 2 where B has intermediate values, and then region 3 where B is huge. And this is called saturation kinetics. And this, you've probably heard about this before in biochem. But this has implications for the SN1 reaction. So let me show you a classic SN1 reaction. Here is your alkyl halide, A. It's in and I got to check the time to make sure we're okay. It's in equilibrium with intermediate carbocation I and product 1, which is the Br minus molecule. So that's P1. And then in the second step, intermediate I reacts with second starting material cyanide with some rate K2 irreversibly to give us, making stuff up at this point, product 2. Okay, all we've done is just put faces on A, B, product 1, and product 2. Okay, so in the case of the SN1 reaction, the expression that we derived up above should be our rate law, okay? But at any given time, for the SN1 reaction, the concentration of your product, 1, which is the concentration of Br minus, should be small. And the rate, and therefore the rate of the backwards reaction. Oh, and then if you look at a conventional SN2 diagram, SN2 energy diagram, K2 times B should be a whole lot bigger than K minus 1 times P1. All right? What that means is once we get to that intermediate, the K2 times concentration of B term, especially if we have an excess of cyanide, will overwhelm the K minus 1 times P1 term, and then our rate constant is going to reduce to the much, oh shoot, Joshua, getting confused. If that's the case, then we forget about the P1 term, and then the dependence on that second step at all falls away, and you're left with the conventional rate expression for the SN1 reaction, which is that it only depends on the rate of the leaving group leaving and the concentration of your starting material. Okay? So if you've ever wondered why in the SN1 reaction, even though the product involves cyanide, you're basically told you don't even have to have cyanide there to get product, the answer is, of course you have to have cyanide there, and of course cyanide is part of the rate law. It's just that the reverse rate of the reaction from the intermediate to starting material is small, and the rate of the forward reaction from intermediate with cyanide to product is fast enough that the cyanide terms cancel out of the equation entirely. Okay, so in terms of saturation kinetics, in the SN1 reaction, the reason we don't see any dependence on cyanide concentration is that we run these reactions in this saturation regime where changing concentrations of cyanide doesn't make any difference. Okay, yeah?
Yeah, we see a number of reactions that are 0 order.
Yeah.
That's why this happens.
Yeah, this is an example of a reaction that is serendipitously 0 order in a reagent that is nonetheless important for the reaction to happen. All right, unfortunately, we got more to do in Chapter 7 that's important. It appears to me now that our syllabus was wildly optimistic in terms of how much we would get to this semester, but this stuff is important, so we'll take the time that's needed. I will see you all tomorrow.